reporter.
So the opponent would like to challenge problem 15, boycott effect.
We reject. Okay, reject.
So the reporter would like to challenge number 2, ready disk.
We accept. Okay. So number 2 is please write down the representative name of your team on the board.
Hello, honorable jurors and fellow competitors. I'm the reporter from Team Excel here. I'm going to report problem number 2, relay disk. Here's a problem statement. A disk suspended vertically by a thin thread is placed in an acoustic field. This device can be used to measure the intensity of sound by turning about the axis of the thread. Investigate the accuracy of such a device. And we mainly focus on why will the disk perform a turning in the acoustic field, and how to define the accuracy of such method to measure sound intensity. And this is my outline. First, I'm going to talk about my preliminary experiment, which is about the observation video, qualitative explanation, and the definition. And second will be theoretical model. It's about the Bernoulli's principle and acoustic intensity. And the third one will be experiment and discussion. We will have the experiment about our setup and variables, and we will have a discussion about the accuracy. And last will be conclusion. This is my preliminary experiment. As you can see, in this observation video, when the sound intensity increases, the tilting angle will also increase too. And in the graph, you can observe this phenomenon, that the angle changes with the sound intensity. And this kind of phenomenon happens because the sound wave cause the air to vibrate and cause the airflow. When the air flows over the disk, it will cause a pressure, and it will generate a torque and let the disk to rotate. It's because that when the air flows over the disk, the flow velocity will decrease, and it will cause a pressure difference on each side of the disk, and so it will generate a torque, pressure torque, and let the disk to rotate. Then when the disk comes into a vertical condition, the pressure on the two sides of the disk will be the same, so it will reach the torque balance. And we define that the first sound intensity that the disk to rotate as a minimum decibel, and let the disk and we define the first sound intensity that the disk to reach tilting angle reach 90 degrees as a maximum decibel. And we also define a phi max as this. And we simplify this, the rotation of the disk like this, and we can get the summation over torque is Fr sine theta. So when the phi max happens, it means that theta is 0, and the summation over torque will be 0, so the disk won't rotate. And next is the theory part. This phenomenon only happens when the wavelength is way bigger than the disk radius. And by the Bernoulli's principle, we can get the pressure acting on each point of the disk. And by integration, we can know the torque. We can know the torque of the disk. It is this. And since the airflow velocity will change by time, so we use the root mean square velocity to measure it. And when the disk remains in an equilibrium position, the pressure torque will be equal to the stress portion. By calculation, we can know the square of root mean square velocity, which looks like this. And we also know that the sound intensity will be proportional to the square of velocity, and we know that the unit decibel is the comparison of the sound intensity. We substitute this into the sound intensity, and we can get the decibel also look like this. And next is the experiment part. We use the signal generator to create the signal, and use the amplifier to amplify the signal, and connect it with a loudspeaker to create the sound wave. And we use a resonance to concentrate the sound wave, to let the disk put it in front of the resonance to rotate. And we also use the sound absorbing sponge to absorb the environmental noise. And this is our experiment equipment. And first, we have to measure the torsion constant. We use to measure the torsion constant by connecting a metal ball on a thin thread to measure it. We let the metal ball to rotate and to measure its rotational period. And we know that the rotational period, and we also know that the moment of inertia. Thus, by calculation, we can get the torsion constant. And first, we change the intensity of sound and to measure its different tilting angle. And in this graph, the red line is the theory line, and the theory line was by this equation. And in this graph, we compare the experiment data and the theoretical value. So we get that when the experiment data and the theoretical values deviation is smaller or equal to 1 degree, and then we put this into the equation, then we calculate the sound intensity, and we can get our accuracy. This is 1 degree is because that a significant figure is 1 decimal place. So this part is 1 degree. And first experiment we done is the initial angle. We change the initial angle to measure the different sound intensity, to measure the different tilting angle in different sound intensity. And this is a graph. As you can see that when the tilting angle increases, the accuracy of the disc, we get that the maximum decibel will decrease. And it can be explained by this equation. It's because that the turning of the angle decrease, so the needed torque will be smaller. And since the needed torque will be smaller, so we can get that the velocity, the square of velocity will be smaller, and the sound intensity will also be smaller. And we also investigate its sensing range. So by this equation, we can get that when the initial angle increases, at that moment the torque will increase. So when the initial angle increases, the sensing range, which is this part, will be smaller. And the second experiment is about the radius of the disc. We change the different radius to measure its different tilting angle in different sound intensity. In this graph, you can see that when the tilting angle is the same, when the radius is bigger, the needed sound intensity will be bigger too. It is because that in this equation, when the radius increases, the needed torque will also be increased. So also the square of velocity will increase. So the needed sound intensity will increase. And we can observe the sensing range. So we know that we observe this. When the sound intensity is the same, the radius of the disc increases. The needed torque to change the same angle will increase. So the turning of the angle will decrease. And the next experiment is about the torsion constant. We change the thin thread to change its torsion constant, and we measure its accuracy of the disc and its sensing range. As you can see in this graph, and this is a torsion constant. When you can see in this part, when the torsion constant is bigger, there will be more deviation than the theoretical value. So the torsion constant will affect the accuracy. And also you can see this the smallest torsion constant will have a small deviation with the theoretical value. And by this equation and this we can know that when the torsion constant increases, the changing of the angle will decrease. When the sound intensity is the same. And next is the conclusion part. When the sound wave causes the air to vibrate, you will have an airflow. When the air flows over the disc, it will cause a different velocity on the two sides of the disc. So it will generate a pressure torque to let the disc to rotate. And when the disc is at a vertical condition, the flow velocity on the two sides of the disc will be the same. So it will reach the torque balance. And we define the first sound intensity like that the disc to rotate as minimum decibel, and we also define the first sound intensity like that the disc reaches 90 degrees will be maximum decibel. And we can simplify the rotating of the disc into this into this. And we know that the summation of the torque will be FR sin theta. So when the phi max happens, the summation of torque will be 0, so the disk won't rotate. And by comparing the experimental data and the theoretical value, we observe a deviation for about, we define that about when the deviation is smaller or equal to 1 degree, and we put this into the equation that we calculate the sound intensity, we can get the accuracy of the sound intensity by measured by this device. And we can get, and when the tilting angle increases, the maximum decibel will decrease. It is because that the turning of the angle will be smaller, so the needed torque will also be smaller, and also the sound intensity will be smaller. And the sensing range will decrease when the initial angle increase. It's because that when the radius of the disk is increased, the needed sound intensity to reach the same tilting angle will also increase. It's because that the needed torque will increase. So the changing of the angle will decrease. And in this experiment of the torsion constant, we observe that when the torsion constant is bigger, the deviation from the theoretical value will decrease. So it will increase. The deviation between the theoretical value and experiment data will increase. So it will affect the accuracy of this device, and it will not be. This device cannot be detect the sound intensity. And this is my end of the report. Thank you.
Moment.
The first question: how do you define your accuracy of the device?
We define it by calculating it. We define the new decibel in this part, and by calculation we can get this. Okay. By putting the 1 degree I have shown in the experiment.
Okay, so
we will get this.
Okay, thank you. So for the next question, will frequency affect the accuracy of your device? The frequency of the sound?
I think the frequency of the sound will affect.
Okay. So the next question is, what is the acting force for your disk to vibrate?
It's a pressure torque.
Okay. So for the will the geometry of the disk affect the experiment?
I think it will affect.
And do you calculate the Reynolds number for your experiment?
I didn't get it.
Okay. So for the next question, do you observe a tilting direction in the z-axis direction in your experiment?
No, because we have fixed the thread in this part, so it will have only this axis rotational and this axis.
Okay, so do you attach your string on the lower side of your disk?
Yes.
Okay, so I have a question. So this will vibrate in the XY direction. Is it correct? Only vibrate in the XY direction and no tilting motion.
Yes.
Okay.
So that is why. So since it will vibrate, so we use the root mean square velocity to express its velocity.
Okay, thank you. So this is the end of my question.
please start.
Honorable jurors and fellow competitors, I'm Chen Ankai from Jingcheng High School, and today I'll be an opponent for problem 2, braided disc. So here's a problem statement. A disc suspended vertically by a thin thread is placed in an acoustic field. This device can be used to measure the intensity of sound by turning about the axis of the thread. So investigate the accuracy of such a device. So main focus of this problem, we think, firstly, we have to construct a measure sensing device, and second, it is the clear definition of the accuracy, which I think the reporter has done very well. So now it's the structure of solving problem. So for the observation video, I think they gave a great clear video and a qualitative explanation of the problem. So for the theoretical model, they use Bernoulli's equation to calculate the pressure torque and the sound, and they get the sound intensity of the torque and how it will affect the angle of the braided disc. So now for the setup, they use an amplifier to produce their sound, and a resonance tube to make sure that the sound is very clear, and they also attach a disc at the end of the resonance tube. And for the experimentation, they did some parameters like they test the torsion constant and how it will affect the angle of the braided disc, and they use different torque and they change different sound density. So for a conclusion, they find that the radius increases, the theta of the radius also increases, and the theta is smaller than 1 is more accurate, and the torsion constant will affect the angle. So here are some strong and weak points. Firstly, I think the reporter did a great job at defining the accuracy of such a device, which is what the problem statement told us. And they gave a clear introduction to the problem, and they used a sound sensor to quantify the results. And they used experiments to verify the theory regarding moment inertia, angular velocity, and sound intensity. So some weak points, the opponent think that they missed some address of some physical phenomenon, like a frequency of the sound and the viscosity of the sound. And I think they have no theoretical condition in the Z-direction torque and the contact friction of the rod, and also the Reynolds number. And we also think that they have lack of investigation on the sound frequency and the geometry of the disc, such as the thickness of the disc. And they have inadequate experiment verification on the sound frequency and the torque value. So these are some points to be discussed. First, I want to talk about their observation video, like where is the camera placement and the contact disc point. And for the experiment setup, I will talk some about like the sound generator and the attach point of the spring, and whether and then how they observe the vibrating motion, and how they get the theta of the braided disc. And for some theory, I'll talk about some energy analysis and discuss with the opponent like how the driving force of the braided disc and the torque and the friction of the rod, how it will affect the rotating motion. And some effect of the parameters that I will discuss with the report later, like the Reynolds number and the viscosity of the air, and whether the temperature of the temperature and the moisture of the air will affect the experiment. And I'll also talk about some disc geometry, like the thickness of the disc and the radius of the disc. So now I would like to invite the reporter to discuss with me. Okay, so can you please continue the observation video? So may I ask where is the camera placement?
The camera was placed on the top place, so you can see that. So you can see the real tilting angle of the disc.
Also, it is at the same position as the thread like from the down to the bottom.
Yes.
And so you use a camera to record the motion and you get the theta angle, right?
Yes.
Okay, so how big is the theta angle? Approximately how big is the theta angle?
You will show you this graph.
Okay, so now I want to ask the. Also, you contact the disc on the top of the braided disc, right?
Yes.
So May I draw the blackboard?
Sure.
Okay, so, if you suspended your disk, like let's assume that this is the x and y, and there, so you suspend your with a thin rod right here, right? Oh, so there are two contact. Oh, so no, I know. So I have understand the setup. So initially I think that there will be, because Z direction on here, if you only contact one rod, and so it will cause a Z tilting action. So
I think we also, if we don't put this, we will also consider. But since we have suspended like this, so we will only consider x and y axis.
okay, so how do you contact the disk with do you contact with adhesive materials? Tape or
We consider. Do you mean by fix with this thread?
yes, but which material?
We use a glue.
Oh,
so you won't affect a lot.
So it won't affect that. So do you try to consider it in your theoretical model? Like the friction will affect the tilting motion.
We have measured this mass, and you won't affect a lot.
Okay, so like so it has small effect.
You will have small effect on this.
Okay, so you use a resonant tube over here, and what is the length of a resonance tube?
The length of a resonance tube was being shown in the experiment, which is 33 centimeters.
Right, 33 centimeters. So it has a range between the discs. So do you think that it will cause some it won't be like a laminar flow? So do you try to calculate the Reynolds number?
It will be placed in this place. So it won't affect a lot.
Also, but did you do experiment on the Reynolds number?
No, I didn't.
Okay, so so the opponent think that they should, although they use a resin tube to decrease the deviation, but I also think that it's important to consider Reynolds number in the tube. So now let's talk about some parameters that may affect the experiment. So how do you think that the thickness of the disc will affect the result?
As being shown in this graph, when the thickness is high, it will affect its accuracy because the thickness of the disc will let the turning become will let the tilting angle become smaller. So it will be not easy to investigate its tilting angle.
Okay, so there is a critical angle. There is a critical thickness to observe the accuracy, right?
Yes.
Like, so the thinner is better.
The thinner is better.
Okay, I understand. And how about can you talk about the theory, like the pressure torque you're talking about? Okay, so the pressure torque. Okay. So pressure torque. So the pressure torque will affect the tilting angle of the device.
Yes. That's the main reason that caused the disc to rotate.
Okay, so why? Because why didn't the disc go all the way around and it just go like moving forward and?
Because this disc has a small deviation, so it won't rotate like this.
Also, if I use the sunlight is very big, and will it start rotating in the center?
It will not start rotating in the center. Yes, because the strings torsion will also have a torque.
So do you think that because I think that the sound is like a wave goes back and forth. So do you think this is the main reason that it won't go like rotating around?
Because the sound wave will move. The sound wave will move back and forth.
Okay.
So we use the root mean square velocity to express the velocity of the sound.
Okay, so do you change the temperature in your experiment? Like
we have controlled our temperature in the same temperature.
Okay, so About the moisture, do you think that the moisture will affect the experiment?
We have also done the experiment in one phase, and we have considered this moisture to be the same.
So can I turn to a page of your experimental results?
You mean what experiment result?
Like a portion part.
Like this?
Okay. Like the next page. Yeah, that's fine. Okay, so also you also change the different portion constant.
Yes.
And you can get the smaller portion constant will be more accurate, right?
Yes.
Okay, so the angle that the disc is tilting, do you think that the bigger the tilting will have a more accurate or smaller tilting will be more accurate?
The accurate will be caused by this. You see that this it has a big deviation, so it is inaccuracy. It is inaccurate.
Also, so we can see that what is the green dot?
Green dot is a jewelry string.
Also, like when it is bigger than this value, then it will start to have a big deviation.
Yes.
Oh, okay, I understand. So we know that the smaller the portion constant, it will be more accurate of the disk.
Yes.
Okay, then I move to the previous page. And okay, so I want to discuss more about the accuracy of the disk. So the accuracy of the disk, you say it is the alpha value. Can you explain the alpha value again?
This alpha is torsion constant.
Oh,
this alpha is torsion constant.
And also the tau is here is the torque, right?
Yes.
Okay, so I understand now. So the accuracy of this disk is only relevant to the torsion constant.
In this experiment, it is.
Okay, so how about the other experiment? There are other things that would affect the accuracy of the disk.
The radius.
Yeah.
As I have mentioned in the report, the radius will affect the accuracy, will affect the disk.
Also, the radius and the torsion constant will affect the
Yes.
disk. Okay, so what about if I change the thickness of the disk? Will these two things will be like the
It was shown in this graph.
Okay, so the thickness will also be a parameter that
Yes.
will affect
Yes,
the
it will
accuracy of
affect
the device.
this deviation between the theoretical value and experiment data. And so when the thickness is big, it will this device will be inaccurate.
Oh, okay, so for another question is that how about it is not like a laminar flow, like the sound of the flow is like a turbulent? Then do you think that this device will still work in some degree of way?
This device will be somewhat inaccurate.
Okay. So this device is only like if there is like a tube over there, so you can only measure intensity like this way, right?
I think the main reason that affects the detect of the sensing rate of the device will be its radius, will be its initial angle, and also the flow velocity.
Yeah. Okay, so the flow velocity is changed by the amplitude of the sound, right?
Yes.
Okay, time's up.
So now I'll do a summary of my report. Firstly, we discussed about I discussed some about the experiment setup, and I clarified that how they did the experiment by drawing some graphs on the blackboard, and then I explained I discussed with some experiment setup like the attachment of the string, and how they attach the string, and then I discussed with the theory like the torsion constant and the radius and the velocity of speed that will affect the accuracy of the device. And then finally, I discussed with them some of the parameters that may affect the experiment, like the Reynolds number and the temperature which they have controlled, and the thickness of the disk and the radius of the disk. So this is my discussion with the reporter, and I think that we have know more about this problem. And thank you for reporter.
Okay. The reviewer. Show question.
Honorable judges and worthy opponents, I'm the reviewer of problem 2. And the first question is for the reporter. Can you please turn to page 29? Okay, so is kappa considered in the first part of your theory?
It's just to simplify the rotating of the disk. So also the string will have a string torsion. So we use the summation. So we express this as the summation of the torque.
Okay. Will it ever reach 90 degrees in your experiment?
Yes, we have reached the 90 degree. We have reached 90 degree as I have said as I have shown in the report.
How about for the opponent? Did you think it is reasonable to reach 90 degrees in this?
Yes, I think it is reasonable. I agree with the reporter.
Okay, and now as for the reporter again, will the resonance tube increase the volume?
The resonance tube, we didn't trace the resonance tube, so it didn't increase the volume.
Okay. And as for the next question, how did you determine, oh, can you please turn to page 5? How can you determine the line on page 5?
Do you mean this line? It was just a fitting line.
Okay. And did you think the friction influenced the result?
I think the friction will affect. But I think it doesn't affect a lot.
Okay, so did you take those? So you think it doesn't affect a lot, so you didn't take those frictions into consideration, right?
Yes.
Okay. And how about the opponent? Did you think that the friction will influence this the experiment a lot?
So as my discussion with the reporter, he said that the mass of the disk, and he did say that it won't affect in their experiment.
So you
I
also
with
agree
report,
with the
yeah.
okay. Thank you.
Okay. You have two minutes. Okay. Reviewer, check the stage.
Okay, honorable judges and worthy opponents. I'm the reviewer of problem 2, Rayleigh disk. And on the left side, this is the problem that they are talking about. And the reviewer's main focus is how the sound makes the disk rotate and how the sound intense. What is the relationship between the sound intensity? Okay, so I'll first talk about what the reporter said. For the phenomenon part, the inclined angle of this creates the sound. And also, Bernoulli's principle, the sound wave create pressure difference, and the torque and rotate and reach, and they eventually reach a balance. As for the theory part, the pressure applying on each point, and they talk about the ρ square velocity, and then the intensity of the sound is proportional. And then as for their experiment, they talk about first the signal generator, and then second, deviation is smaller or equal to 1 degree proves the accuracy. And third, different initial tilted angle has a positive correlation to torque. And fourth, the radius of the disk. If the radius is bigger, the intensity increases. And last, the torsion constant. If the torsion constant increases, the deviation increases and the change of angle increases. And I'll talk about the pros and cons of the reporter. For their advantage, first, they use clear graphs to demonstrate its results. And second, he takes various parameters into consideration. Third, he uses clear pictures to simulate. And fourth, he uses devices for his experiment. And for his disadvantage, they lack the statistics of the results. And second, he didn't give detailed introduction about the formula. And third, there are few theoretical and there are more consideration they can use in their theory. And as for the opponent, he talks about what the reporter said, and they also discussed about some problems. And also, now I'm going to talk about the pros and cons of the opponent. As for the opponent's advantage, he talks about some parameters that will affect the result. And also, he put forward several specific questions worth discussing. As for the disadvantage, he misunderstood the content of reporter's presentation. And now I'm going to talk about their discussion. First, the opponent asks, how did the reporter suspend the disk? And the reporter's answer is, they used a string to suspend it. And then the next question is, the opponent asks, can the reporter explain the alpha? And the reporter answer is, alpha is the torsion constant. And the next question is how the thickness, the opponent asks how the thickness will affect the results. And the reporter answer is, it will let the angle become smaller. And next, the opponent asks, did moisture or temperature affect the results? The reporter answer is no, because they already check it through before the experiment. And then next, the opponent asks, will other factors affect the accuracy? The reporter answer is, the radius will also affect the accuracy. And then my question to the reporter is, will it reach 90 degrees in the experiment? The reporter answer is yes. And also the opponent answer is, it is reasonable to reach 90 degrees. And my question to also the reporter is, do you think the friction will affect the experiment? And their answer is, it doesn't, because it's too small. And this is the end of my presentation. Thank you for listening.
Okay. Thank you.
And this is a concluding and remark for the reporter. At first, we doesn't need to consider this y-axis tilting, because it only vibrates in the xy axis. This is because that we suspended and we fix the disc from the top to the bottom, so it won't have the y-axis tilting. And in the second point, we did investigate how the thickness affect the accuracy and the tilting angle. In this graph, you can see that the thickness, when the thickness increases, you will have bigger deviation at this part. So it will affect its accuracy, and this part will be not. This part will be not accurate. And also the viscosity, the third point, the viscosity of the air, the mass of the disc won't affect that phenomenon so much. And fourth, the smaller the torsion constant is, the more accurate the disk will be. We can show it was shown in this graph. When this torsion constant is smaller, and you can see the very small deviation with the theoretical value. And in the fifth part, when the turbulence flow, the disk will somehow become inaccurate. It is because that the turbulence will affect the pressure acting on the disk. So it will have some unstable situation happen on the disk. So it will affect its accuracy. And I would like to talk more about the thickness of the disk. And in this graph you can see this phenomenon, and in this theoretical value also you can see this, and you will have a boundary limit.
Okay, time's up. Okay, overall, any questions? Please.
Could I request the reporter to show me the presentation on page, say, maybe 37 or 25? You mentioned the fishing line torsion are far off, right?
Yes.
Could you offer me some kind of interpretation or even guessing how would that happen?
Do you mean the
fishing line, the data?
The data of the
Why the experimental data of fishing line is far off from your theoretical prediction?
Because it has small tilting angle, so when the sound intensity was changing in a small part, so it will not be easy to
But
observe.
I mean, if I remember, the thickness part has the similar, say, tendency.
Yes.
Yeah. So
it is also that the tilting angle will be very small, so it is not easy to observe, and it will cause the inaccurate of the
okay,
reference.
I think I get it. How about the opponent? Could you offer some kind of insight?
Yeah, I agree with the reporter. Like the thickness got bigger, so the mass got bigger, so it would like rotate like the smaller, so it would not hard to define that the difference between different intensity to like different angles, so it may cause some deviation to the accuracy of the disk.
Okay, I get it. How about reviewer? Do you have some kind of interpretation or not?
I agree with the reporter said too, because it only tilts at a little bit, so it doesn't really, and when the intensity increases, it doesn't really affect.
Okay, thank you. At the
Okay, any other questions?
Can clarify some basics. So what's the initial position of the disk?
The initial.
So
In this part, we have done an experiment about this.
no, I need to see the setup.
This
Yeah,
part.
maybe this one. So is this the initial position?
It is just to demonstrate our experiment setup. So it will not be the real condition of the disk.
And the sound wave just hit it.
Yes, the sound wave just hit it and cause a pressure difference, and we will generate some pressure to let the disk.
It always rotates at the same direction, or sometimes it rotates at the opposite direction.
It will only rotate in the same. It will only rotate in the same direction, because we have controlled its initial. We have controlled its initial. We will have controlled its initial angle, and it will tilt at the same direction. So it will not rotate like a round.
So initially it's slightly tilted already. Initially, it's parallel to the edge, or it's slightly.
No, it's just to demonstrate. We have done an experiment about the tilting angle and use a backboard.
Sure.
I just want to know, initially it's, for example, this is your tube, right? It's perpendicular to your tube, or it's slightly.
You will have a tilting. You will have an initial tilting. It will not parallel. It will not parallel to the tube, because then if the disc is parallel to the tube, it will immediately reach the boundary condition of this device. So we can measure it.
On page 9, you have a root mean square of velocity.
Yes.
What's the value of this?
The root mean square velocity will changes by the sound intensity. This is the square of velocity is proportional to the sound intensity.
Do you have a numerical value of this quantity?
It will changes by the sound intensity. So I have done the several experiments about this.
Is it the velocity of the sound or not?
It's the velocity of sound. By giving its average, so we get the root mean square of velocity. Since the airflow velocity, since the sound is a wave, so it will sometimes high and sometimes low. So we use the root mean square velocity to measure its airflow velocity.
That's the velocity of the vibration, not the sound.
It's a sound. It's an air velocity. Yes, it's a sound air velocity.
Okay.
Okay. Anything else? No. Okay. Thank you. So please prepare your score. Ready? Okay. For the reporter. Okay, 7, 7, 8, 6, and 7. For the opponent, 6, 7, 5, 7, and 7. For the reviewer, 6, 7, 7, 6, and 6. Okay, so that concludes this stage of fight. We have 15 minutes break.